Well, what can I say? I'm so happy to be here. That is, it's beyond words. So when I met you, Yakir, it was long ago. I don't even want to think how long. I think that was in '85, which gives us. You were, yes, yes. And I already told you many things yesterday. When we discussed about Yakir, how I met him, and so on and so forth. So I don't want to waste your time on that. Of course, we worked together on many things, but as also Lenny said, apart from the thing that we actually worked together, there were so many other things that you inspired me. So I decided for today not to talk about something that we did together, but something completely different. Nevertheless, that was inspired by perhaps one or two words that you said at a certain moment that I remembered pretty well. So my talk today, let me tell you what the acronyms TBD stand for. They stand for Entanglement and the Foundations of Statistical Mechanics. Okay, yes, Shmuel. So, well, statistical mechanics has a long history. I don't have to tell you how important it is. And even before quantum mechanics, so in classical mechanics, statistical mechanics was a wonderfully successful theory. It explained an enormous range of phenomena. And we actually see statistical mechanics at work every time. So I don't know. For this audience here, I would say all phenomena like this, if I leave my cup of coffee on the desk, I know that after some time it will cool down at room temperature. If I leave my beer, it will warm up at the room temperature. By the way, this cannot work in England because there are people drink tea to start with, and the traditional beer is in any case at room temperature. So what can I do? So, but you really see phenomena that are related to large number of particles interacting at work all the time. And what is the most important thing about this is that you don't need to prepare the system very carefully as in all kind of experiment. Bring any cup of coffee and you will cool down. You don't need to take care of exactly how the air in the room is. You just give a few macroscopic parameters and you will see the same phenomena repeated. So it is a very robust sort of phenomenology. And people were able to put that into equations and find all kind of the equations that describe with very good accuracy what is happening. On the other hand, the moment you really go down to the foundations, you see for the classical statistical mechanics, you see that the situation is not very clear. It's not very clear. So for example, if I have this cup of coffee, can I tell from first principles that if there are some conditions fulfilled, I will solve Newton's equation, and I know that it will come at equilibrium at room temperature? I don't need to actually measure and see where they are, but at least a statement that if such and such happens at the microscopic level, I'm guaranteed that it will reach equilibrium, or any statement along those things. There is nothing like that in classical statistical mechanics. So how does it work? Well, it works because people found some rules of thumb that, in addition to just Newton's equation, that seem to do the trick. So for example, one of them is the so-called Gibbs ensemble. So instead of looking at one cup, Gibbs said, okay, let me take an ensemble of cups of coffee and see what happens on that ensemble of coffee. So this is the famous Gibbs ensemble, and you would make an average on them. How type of average? How do I select them? Well, it's this well-known equal a priori probability. So different situations that correspond to the same macroscopic rule, I should put in my ensemble with equal probability. But of course, I'm interested in this one, the one that I have, not in an ensemble. I'm not going to drink so many. In fact, you know, for this trick, they are empty. But now, how do you justify this equal a priori? Well, one way to justify would be to say, look, suppose that before I leave it here in connection with the room, I just pour the coffee in, I isolate, and I keep it for some random time. And then I select, you know, the situation after some time. So then there is this ergodicity thing, which tells that the state evolves, and eventually it comes close to all possible states that correspond to those parameters. And that would be the justification for this equal a priori thing. Now, under which condition ergodicity works in classical mechanics? Well, this is a very tough problem, and as far as I'm aware, perhaps one or two systems were shown to be ergodic, but not in general. Definitely not the entire range of systems that we know. So where comes Yakir in all this? You see, already in '86, when I was there, Yakir was by that time teaching only 2 different lectures, which were in this good tradition of Yakir the same, only that one year they were called measurement theory in quantum mechanics, and the other year were called paradoxes. And I remember that Yakir was, at a certain moment in one lecture, he discussed EPR with 2 singlets, and he was very careful, and probably one of the very few places in the world in which Yakir mentioned that you have subjective lack of knowledge when somebody, Bob, measures the particle, but you don't know what the result is, and objective lack of knowledge when it is still entangled. And, you know, I knew this thing very well, like Lenny said, that you may know everything about a system, but not everything about parts. But the way in which you said, you know, make the things absolutely clear in my mind, the difference between subjective and objective. And perhaps at some time you also mentioned that perhaps looking from the quantum mechanical point of view, where there is objective lack of knowledge, I don't need to do all these rules of thumb, but have a much better understanding of the phenomena. So what I want to tell today is the following. Here is the framework that I do. I have a system, which is my cup of coffee, and I have an environment. Let me call E an environment. And they live in the Hilbert space, H system cross H environment. And I will consider some pure state, psi, of the system and environment. And I want to know what happens with my little system as this wave function evolves in time. Okay? So my aim here is to see what happens to rho of the system, which is the trace over the environment of the rho system environment, which is nothing that the trace over the environment of psi, you know, time t of system environment of this pure state. And I want to know how this function rho of t evolves. So what is the main result? The main result is that when the system is much smaller than the environment, and I will tell that in more details what I mean, for almost all Hamiltonians that you can imagine, and for almost all states that you can imagine, the system will reach equilibrium. And I will prove that directly from Schrödinger equation with no other assumption. No averages, no nothing for this particular thing. Okay, that is the main thing. Now, before showing that, I just want to make sure that I'm on a good track at all. You see, this principle of a priori equal probabilities worked very well classically. So if I want to throw it out and then just concentrate on one particular state that it evolves, you know, I should know that I'm allowed to throw it out. You know, I'm not missing too much. So first, just a result, it will not be used in my main proof, but just historically, it was the first thing that we did, just to see that we are on the right track. We found something that we called canonical typicality. And here it is. So suppose I have two systems, S and the environment, and overall they are in a pure state. Now, generally, you would say in statistical mechanics, let me define some macroscopic parameters for the thing. For example, the volume, the temperature, and so on. So I say that the state psi, which belongs to this Hilbert space, Hs cross He, in fact belongs to some restricted subspace. So instead of defining temperature, defining everything, I just say it belongs to some restricted subspace, which is included in Hs cross He. What particular should I take? Well, sometimes people take microcanonical, where the energy is well defined, or canonical. I will not make any sort of assumptions about that. Just any restricted Hilbert subspace. Okay? So imagine that we have this big Hilbert subspace that is Hs cross H environment, and I have some restricted subspace here, H restricted. Now,
Sandu?
yes?
This restriction, whatever it is, remains a restriction even when you switch on the coupling between the system and the...
I'm not talking at this moment the dynamics. Dynamics will come in second part. That's a very good question. At the moment, I say for the initial conditions, some restricted, which may be composed by entangled states. And entanglement will be the key of what we do. So that is it. Now, if I wanted to do the equal a priori probability to choose states from here, then what I would have to do, I would have to take the identity over the restricted subspace. Okay? Well, 1 over n, whatever is for normalization. So forgetting this thing. So I want to take the density, some density matrix that is the identity over the restricted subspace. That is what people would do for if I were to pick states at random uniformly on the Haar measure from this thing.
So finite Hilbert space altogether?
I will take a finite Hilbert space. Yes, definitely. Yeah. There will be some niceties for infinite Hilbert space. I haven't done them. So finite Hilbert space, but as large as you want. Now,
Sandu, I have a question.
yes.
Yeah. In that way, yeah. How much side of the Hilbert?
How much?
How much side of in that the sum of even in the finite size Hilbert space, in that the only the dimension.
I will come to that. I will come to that. I come to that, yes. So if the system and the environment are in the identity, then I would have some state that I call omega of the system that is trace over the environment of this identity over the restricted subspace. And I will call that the canonical state. So this is for me the canonical state. Is it Boltzmannian? Well, no. There is no reason for it to be Boltzmannian because the restriction is not one of those standard ones. I just take any arbitrary restriction. So being an arbitrary restriction, this is the meaning. This is the state of the system, the mixed state if you were to pick and average states at random from this thing. Okay? But that would be to pick states at random and to average. So here is a nice result. Come and pick an individual state. Okay? And check what is the density matrix rho S of that particular individual state. Okay? So here is the result. This rho S for almost all states there will be almost identical to omega S. So it doesn't matter what individual state I pick for the whole thing, it will be close to the canonical state when? When the dimension of the Hilbert space of the system will be much smaller than the dimension of the Hilbert space of the environment. The bigger this discrepancy is, the closer these two things will be. Okay? So if that is the case, then it means that I can refer, that I'm on the good track. I can refer to individual states, and I don't need to average. So before showing you that, let me give you some intuition why this would be approximatively equal to that. Just to see how the whole idea of Hilbert space work. So let me take for simplicity that I make no restriction whatsoever. So suppose there is no Hamiltonian, so all states, say states of spins, I have n spins, and up and down on the z-axis are equally probable. Okay? So in that case, let me look, say the system, suppose my system is spin number 1. I will not even take many spins for my system. I have a cup of coffee of one single atom. So it is possible that it will be up. Or it is possible that it will be down. And in fact, there are many states of system. This is the system. And then I have to have environment. So I could have up of the system and some state phi of the environment. Or I could have down on the system and some other state phi prime of the environment. Okay? If I pick all states at random and all of them are equally probable, I want that omega of the system is just the identity on the system with probability half up, with probability half down. Now, this particular state, if I look at the system itself, the density matrix of this particular state on the system is up, is very far from being identity. The density matrix of this one is down. Again, it's a pure state. Is very far. So by no means the density matrix of the system in these two particular states is close to identity. But there are other states. So for example, it is possible to have up times some state psi plus down some state psi prime. Okay? There are states like this. So the claim is that sort of states like this are far more probable than states like those. And let's see why. And let's see how they depend on the size of the Hilbert space of the environment. So suppose that this is made out of n spins. Overall, I have n plus 1. So the dimension of the Hilbert space to which this one belongs is 2 to the n. Okay. So how many states I have overall that the first spin is up and this spin, with the first spin up? Well, I can pick this one anywhere in a 2 to the n dimensional space. Similarly here. But let me see of something like this, where the only constraint is that phi prime is orthogonal to phi. So I can pick this one wherever I want from 2 to the n, and I can pick this one wherever I want from 2 to the n minus 1, just to be orthogonal. So it is exponentially more likely that I will be in an entangled state.
Sandu,
Yes?
would it be correct to say that a condition for the validity of your theorem is that you consider states where which reflect entanglement between the system and the environment?
Yes, yes, but I haven't stated yet the theorem. So I just told you qualitatively. But let me tell you what the actual theorem is. So the actual theorem is general. So here it is, and this will show all kind of elements that I will be using in the thing that I really want. This is, in fact, just the initial one. You see, they will not be the same, that is, rho of the system, in general, not is identical to the canonical state. But most of them will be approximate. So what do I mean to be close to this? I need some distance. So I want to define a distance between the canonical state and some arbitrary state rho of the system. What distance shall I use? I will use norm 1. So I will use 1 over 2 trace of square root of omega minus rho square. This is a very, very good distance. Why? Well, this time Hermitian conjugate, but they are Hermitian in any case. Why do I use this? This is a number, d, that is between 1 and 0, and the value of d represents what is the maximum probability to distinguish rho from omega if you do the best measurement possible for distinguishing. So when they are close, it is very difficult to distinguish. When they are far, this is the strongest distance that you can imagine. It's not easy to work with, although there are some tricks that we used, but that is the thing. So what is that we show? Well, we show the following thing. Let me look at the average distance, omega s rho, when I average over, well, omega s and rho of the system when I average over all states psi from H restricted. Well, this turns out to be smaller or equal than 1 over 2, the dimension of the system square over the dimension of R, the dimension of the Hilbert spaces. No, not squared. You see, this, if R would be a direct product of the two subspaces of the system and of the environment, this would be ds times d of the environment. So this effectively would be ds over the environment. But it might not be, because if I take entangled states, it crosses. It's not a direct product, the restricted space. But you see, if I have the number of spins here much larger, this is exponentially much larger than ds squared. So what does it mean? You see, the distance is a positive number. So if the average of all states psi is very small, it means that the distance of almost all individual from that is very small. Okay? So that means, and the larger the environment, the smaller this distance is. So it means that if you pick at random, with exponentially small probability, you will find something that is not the individual state typical. So this shows me that I'm on the good track. I don't need to make these averages. I may pick individual states and look at what happens with an individual state. So this was like a preparing exercise. But by itself, so we discovered this together with my, my two collaborators, with Tony Short. He was my postdoc, and now he is my colleague there, and with Andreas Winter. Was our colleague at the time, then moved to Barcelona, and now I heard that he moved from Barcelona away. Okay. At the same time, I think that almost simultaneously also Joy Lebowitz and Shelley Goldstein and Tumulka, they found the similar notion. They called it canonical typicality. You can say more. We actually said more than what they said. We said what happens for the states that are not below, how few they are. Well, they are double exponentially few. So something that the volume of the states where the distance between rho and omega is different, it becomes virtually zero.
The dimension of the environment can be arbitrarily large. You declared all the universe to be the environment. What really fixes for you an environment?
Look, suppose I take here, I just made an exercise. I isolate a system, I have an environment, I have this. And I pick states at random. Of course, if you ask me here, do I pick a state of my universe? Well, I'm not picking a state of the universe. But as a matter of fact, this is how it works. If you were to pick at random states, this is what you will get. Now again, the state that I'm interested in is not random. It's the state of this coffee, which by no means was a random state. And it's due to the fact that the universe started in a low entropy. If that wouldn't have been the case, the coffee here would have not been picked by humans, because humans would not exist, cups of coffee would not exist, and I will not be here to talk too much about it. Okay? So states of interest might not be typical, but, and in fact are not typical. But this is to say that in many instances I don't need to use averaging, because I can do with, during the evolution it may become typical. So I'm on the good track of doing that. And now, since I established that, you can forget everything about this, because I will not actually use it as such. So now I will do I come to the thing that really matters to me. And I want to know how long I still have. Oops, less than I hoped. Right, so what do I want? Again, I have a state psi of a system and environment, and I want to let this evolve in time. Okay? Now, it turned out that if you want to make progress, it pays to be as simple as possible. Okay? And not to get lost in details. So I want to put a system to interact with the environment and see what happens to the system. Will it reach equilibrium or not? Things like this. So what do I mean to be simple? So I can take, for example, some particular Hamiltonian, like spins with near neighbor interactions, which is simpler than spins with longer interaction or whatever. But that is not actually being simple. That will introduce a lot of particularities of that system. So what is simple is to say I pick any Hamiltonian that you can imagine, up to one little restriction. So let me tell you what that little restriction is. So imagine I have a Hamiltonian, and the Hamiltonian has many energy levels. Okay? I don't tell you what the energies are. I don't tell you what the eigenstates are. Just this is the spectrum. It has many energy levels. And here is the demand that I impose. I impose that I do not have two levels here situated at the same distance as two other levels. Okay? So the energy difference between two levels are not degenerate.
To what accuracy?
That's very good. If they are even epsilon different, infinitesimal, I'm fine. Okay? And I will let you know why.
And a given level is also not allowed to be degenerate.
Not allowed to be degenerate. Okay. For simplicity. Let me tell you why this idea came. Suppose I have two systems here that do not interact. Okay? So then this is system A, and that is system B. So then here I may have two states. The energy eigenstates are of the type some AN of system A times AM of system B. They are non-interacting, so I have, and this is in fact some energy En plus Em of the combined system. So if they don't interact, let's look at the following thing. Let's look at E1 for A and some, so let's put E1A, E1B. This has the energy E1A plus E1B. Let me look at E2A, E1B. So this has another energy, E2A plus E1B. But I have also E1A, E2B, which has the energy E1A plus E2B, and in the end, E2A and E2B, which has the energy E2A plus E2B. So now the difference between these two is E1A minus E2A. The difference between these two is again E1A minus E2A. So if I have a system that doesn't interact, two systems that don't interact, you will have enormous number of degeneracies. Because for any state of energy of this, you will have exactly the same spectrum of the other. So I want to, yes?
So was the condition that neighboring levels not have the same energy?
Even if they are not, any two. Any two levels do not have the same as any two levels, any other two, correct. So incidentally, if I ask this, then none of them, that means the system is fully interactive. Because here I split this particular system as that times that. Now this one may be many, many spins, but it means there is no, so for example, they could be, you know, many spins here, and I consider this A and that B. But once I put this, it means that also if I partition in any other way, for example, this to be A and that to be B, they should also interact. It's the same system, only I look it in a different way. So it means I really have a system that is fully interacting. That is a small nicety that I did. Why? Because if I have one region that is totally decoupled, that is how it shouldn't be there. Now you ask up to what accuracy? So here is what I want to do. I now have to be a bit more precise in what I really want to do. And that will come part of it. So when I look at this cup of coffee, which, by the way, by now is colder. Yeah.
That's a proof of your theorem.
That's a proof of my theorem. The phenomena seems very simple. I have a cup of coffee, it thermalized, it reached room temperature. Now, if you are more careful, you can decompose this phenomenon in a few different phenomena. First of all, there is the fact that the state of the cup of coffee will reach a final state and will stay there for a long time with some oscillations. So it will do equilibration. Okay? There is another property of it. The state to which it equilibrates is independent on the precise microstate of the room. There is something else. The state that is reached is independent on the initial state of coffee within some limits. Of course, if this would be so hot like an atomic bomb, it will change the environment. And then there are other things. The state of equilibrium of this will be a Boltzmannian. And I may also think what are the time scales. What is the time scale that it reaches? In my case, it was about 30 minutes. Now, in order to be able to do progress, it was very important that we looked at these particular properties and say, look, suppose I just want to find out that the system will reach equilibrium. I don't ask that to be a Boltzmannian. I don't ask what is the time scale. Okay, I just want to know, will it reach equilibrium? But just give me the conditions for it and solve the Schrödinger equation. Okay? Now, the question that Bill asked, how well I want to avoid this degeneracy thing. If it is almost degenerate, we'll have recurrences, and the time that it reaches equilibrium will become longer. So how closely I do this depends on how much I can avoid all these degeneracies in energy space. But if I'm just interested in equilibrium, it doesn't matter. And what I'm interested in now is what happens on the long time scale. Second thing, And I follow that idea that I want to be as general as possible. I will not put any other restriction on the Hamiltonian. Why do things reach the ordinary equilibrium with Boltzmannian? Because the object has some energy, some Hamiltonian of itself, and also has some interaction with the room. But generally, the interaction is much smaller, and that is necessary in order to do thermalization, but that will not affect the Hamiltonian itself. So, and there I can also hear in the air, the different pieces of the air. You know, this cubic meter interacts with the other cubic meter, but at the surface, that is, you can neglect. But, and then energy is an extensive quantity. You add what is the energy in this cubic meter with what is in that cubic meter with that is in that cubic meter and so on. And it's approximately good. All these are the ingredients that come into fact that this will reach a Boltzmannian thing, or at least I think so. But suppose that I look at some energy, some Hamiltonian that is not screened, long, long distance. Now, you may imagine that, for example, electrodynamics is that because it decays very slowly. But electrodynamics, you have positive and negative charges, so effectively they are screened, and then you just have dipole interaction. But gravity, suppose you have a gas of galaxies. You cannot apply the standard statistical mechanics laws, because energy is not an extensive quantity. Then it doesn't scale with volume, it doesn't do any of the sort of things that we do usually. I can look at spins. So generally you may say near neighbor interaction or I don't know, second neighbor interaction. I can imagine a crazy Hamiltonian in which all spins interact. There is a term in which all of them interact together. Sigma dot sigma dot sigma dot sigma dot sigma, not pairwise interaction. I allow any of them. This is the only condition I impose. Okay? These are the rules of my game. It turns out that if I do that, you can do things very nicely. So again, what am I going to do? Here is the thing. It's a bit similar to what I did before, but there are some very important differences. So I want to look at my subsystem. Now, here is one thing. Because I have a Hamiltonian, evolution is unitary. So what happens with the state of the system, or the full state of system, the pure state of system and environment? It evolves continuously. It never stops. It is a time-independent Hamiltonian. It never, ever stops. In this very big Hilbert space of the system and the environment, it uniformly moves. However, and here is the claim, if I just look at the density matrix of the little system of interest, so if I look at rho s at time t, well, that will stop for some times, although the big state continues to move. Okay? That is the sort of thing that I'm looking at. Okay? And that is what happens, and how it stops, and for how long it stops. Well, stops, I mean, will fluctuate a little bit around some fixed state. How small are the fluctuations, and for how long they are, or for how short time it departs, that depends, well, that depends again on the size of the system and of the environment. I will tell about that a little bit more. So, if it would be to stop, it always pays to make a guess, to know what you are aiming for. So if the state of the subsystem stops and equilibrates, around what state will do that? Okay? So, very simple. So let me imagine first the density matrix of the system and environment, which is psi of t, psi of t. Okay? This goes. And I will be looking at rho s of t, which is the trace over the environment of rho system environment of t. And my claim is that this will be for almost all time around some state. So let me think of the time average of this thing. Let me call omega would be 1 over t rho omega s of t dt. Because if this is to stay around something, it means that the average over all time, it will stay around the average if it fluctuates just a little bit. So this is the canonical state that I aim to show for you that I will be there. Okay? So what am I going to look at? Here is what I'm going to look at. First, I'm going to look at the clock. Okay. Fine. So this will tell me a few things. So again, I want to look at the distance between omega system, this omega system which is the average over time of that thing, where that evolves under the Hamiltonian, and rho of t. Again, the norm 1, the one that I did before, which tells what is the probability of distinguishing this thing. And to make things simple, I would take this and I will average over time.
So Luis, rho?
Rho system of t. Yes, absolutely. Yeah. And I will average over time. If this average is small, it means that for almost all time, they are almost identical. From time to time, it might depart. Okay? Right. So when do I expect this? I will tell you the result. But when do I expect this to be small, and when do I expect this to be large? You see, imagine that this is hot. It's no longer hot, but it was hot. What happened with the energy? The energy went out. And by now, it reaches equilibrium. Now, energy is not the best way to think of, because suppose I'm looking at crazy Hamiltonians. But information about what was its initial state disappeared. It reached equilibrium now. So the information has to leave. But if it leaves, I don't want to come it back immediately, because then I will have fluctuations. It will come back and rewarm and sort of things like this. So that means that the environment must be large enough that the information will just propagate and propagate and propagate for a long time before it comes back. Mm-hmm. Now, so it means that the system as a whole, system plus environment, little system plus environment, needs to go through many, many different states. Perhaps orthogonal states, perhaps not necessarily, but through many, many states. When can it do that? Well, let me write the state psi of t of system and environment. Well, this is sum over n, some coefficient Cn, En of the system environment, and then it occurs phases, e to the I Ent over h bar. So it is a superposition of many energy eigenstates of the full thing. If it would not be a superposition, suppose only one of them, well, then that is really a crazy state, because then nothing moves. So then it is equilibrated from the beginning. But in order to move through many things, it needs to have many energy eigenstates in decomposition. Okay? So that when you average, it goes through many states. Okay? Here is a way to put a sort of qualitative, well, a quantitative bound on how many states it goes. So you see, let me look again at rho of the whole thing, SE, as a function of time. So this is psi of t, psi of t. Bless you. How much does it span? So let me look at this whole thing, and let me do the integral over time of rho S E, function of t dt 1 over t. Let me call that omega of SE. Okay? So I mix states at different times. Okay? I just mix states at different times. If I mix more states, I would have something here that is far from being pure. The purity of this state goes down. Okay? So let me define something that I will call, where do I have space? The effective dimension of the SE space, and say that that is 1 over, so it's the inverse of the purity, 1 over the trace of this omega square. Okay? If omega is, if this is just a single energy state, psi doesn't change, so the rank of this matrix is 1, is just pure state. Trace of omega square would be just 1, 0, 0, 0, 0. Omega square will be just 1. So this would be, the effective dimension would be 1. If it so happens that I mix all of them with equal coefficients, then the density matrix will be 1 over n up to 1 over n. The square of the thing will be 1 over n squared. And the trace of this would be n times 1 over n squared. So it will be 1 over n. And when I divide by it, is n.
But this depends on your initial condition.
This depends on my initial condition, precisely.
It's completely arbitrary.
It's completely arbitrary depending on what my state is. So I will then ask whether this particular cup of coffee fulfills those things or not. So this is the key quantity. The effective space that is spanned by the state of the system and the environment as it moves. And what I expect that when this is small, information goes out and comes back. It goes out and comes back, and my cup will become cooler, hotter, cooler, hotter. It will not equilibrate. When this goes and spends a long time, only then I have a hope for the system to equilibrate. So this is a necessary condition for the system to roughly equilibrate. Is it a sufficient one? Well, here comes the important thing. Yes, it is a sufficient one. That is the thing. So here is the main result. The main result is that if I look at the distance between omega s and rho s, that distance is smaller than square root of the dimension of the system square over the effective of the system and the environment. It could be small, it could be large. So this is the general statement here. Incidentally, what is that? What is that trace of omega square? Well, you do this. You do the average. You have to average this thing in time. When you take the density matrix, you will have things like En minus Em times that thing. And when En is different from Em, that will vanish. So this thing equals, in fact, 1 over sum over n Cn to the 4. Okay? Cn squared will be 1, the sum. Cn to the 4. Right. So here's something interesting. Before talking about anything else, let me clean and have only the results. So I have a bound on the fluctuations. If this number is very large, it could be 1 at most, there is no bound. And I don't know what will happen in those particular cases. If this number is very small, then I know that the state at almost all times is equals to the canonical state. But let's look at what this depends. So let me write there. So this D effective is that. What don't you see here? You know, this is like that case of the dog that didn't bark, okay? What is important is what is not here. Here you see nothing about what the energy eigenstates are. Nothing. It's independent on that, okay? What the actual values of the energy eigenvalues are, that will only determine the time scales, but will not determine on the long time how long this is away from equilibrium. That depends only on how many energy eigenstates are superposed and with what coefficients. It is also independent on the actual form of the energy eigenstates. That doesn't matter. That again, well, that appears in what is omega. Okay, because there you integrate, and this has to do with exactly what the energy eigenstates are. But it does not govern the fluctuations and the fact that they are large or small. Okay? So all I need to know, I have a Hamiltonian that I decide what it is just by saying that has some energy levels that are non-degenerate. And all is important is with what amplitudes I put them together. Okay? Now, Now the time is gone. And I will not prove for you that when the environment is large, much larger than the system, almost every single state will have a large numbers here. Or do you want me to prove that in 30 seconds? Oh, it's simple. But I will say no. OK. So that's it. And thank you very much.
So let's go to the cup of coffee. Oh, sorry.
Yes. So now if you started talking, you say who would ask the questions.
The two cups of coffee. Will they have these
Well,
plateaus?
if look,
Isolated from the rest of the room?
if they are isolated from the rest of the room, in that situation, the bound will not work so well. Okay, even then, because then the most this could be is ds squared. So in that situation, this particular bound will not work. Take 3 cups. Well, if you have 3 cups, then it already works. Because remember, these are dimension of the Hilbert space. Even if they are spins, their n spin is 2 to the n. So take 3 cups, take one of the system to be 1 cup and the other to be 2 cups, you are in business. That's how it works. So it doesn't solve everything, but it solves almost.
Can you measure these plateaus?
Here's something interesting. This is a bound of how, what is the average magnitude of the fluctuation. Now there is something very important to say. If I take, for example, this one to be, say, 3 cups, or even 2 cups, well, even 2 cups works, so 3 cups, 1 is my system and 2 are the others. This number is exponentially small. The deviation from it are double exponential. So if I didn't prove to you, but if I would say, what is the volume of the states that go above this amount of fluctuations, of the points where it goes. So the times where they go, because this is the average. So for almost all times is at equilibrium. From time to time, it goes above. That is double exponential small. So that tells that the usual view that you have these Gaussian fluctuations around equilibrium, that is incorrect. The density matrix of my system, rho of S, barely moves around the equilibrium. What are the usual fluctuations that we see is if we measure what the state is, and because this is a density matrix, I will get one value or another value or another value. But the density matrix itself barely moves. So the view that those fluctuations are dynamic that we see, no, they are just pure random quantum fluctuations that even if the state would be fixed, you would still have them. Okay. Yes, I will come to you.
So let me see how to ask this concisely. This is, first of all, extremely beautiful and extremely profound.
Thank you.
And, it's really lovely. I just want to see which parts of our previous understanding of the foundations of statistical mechanics this overthrows and which parts it leaves intact. And tell me if I'm understanding you correctly.
Yes.
The old-fashioned reversibility arguments
Yes.
are still going to be in place here.
Yes, because we know that they are valid.
That is, you take the time reverse of the final equilibrated state, you allow it to evolve, you'll get disequilibration. Okay?
Yes.
But
Yes.
number or you measure. This is what you meant by referring to almost all of the states.
Yes.
As opposed to all. And the reason it has to be almost as opposed to all is that is the proof that it has to be almost as opposed to all are the reversibility arguments, which are still going to be in place here. But
Well,
if
yeah.
this is right, then one thing that doesn't seem to have changed
Yes.
is that we need some kind of principled excuse for neglecting this very small space of state.
Yes.
And this excuse, I take it, is going to take the form of a probability distribution over states, exactly as it did for Boltzmann.
Yes.
And people like this. Am I right in thinking?
Okay, so you, how shall I say? You looked at many different phenomena, and your question touches many different points. So let me first tell what has been achieved and what not. Okay. So what has been achieved, which is in the first place, is that we were able to separate some aspects of the general phenomena of thermalization. So we could look at equilibration and have a statement of what is the state at almost all times. Okay? But we were able to separate that from how quickly it goes. Okay? That is one thing. The other thing is what has been achieved is that we were able to go beyond thermalization. Being thermal and having temperature and things like this, that is only for particular Hamiltonians where the energy is extensive. And we were able, this could be applied to gravitational interaction or could be arrived to some crazy interaction of sigma dot sigma dot sigma dot sigma, not pairwise. And we enlarge the notion of what is a canonical state. However, for thermalization, to say what is this state, that is known, that is the Boltzmannian. Here we don't know, but we know formally what it is. Okay? So we open some pieces of knowledge that in some sense are orthogonal to the others, that you might be interested on the others. So for, I just want to say what it is. So for example, if this is the distance, and the distance is between 0 and 1, so the distance of my rho from omega will be like this. Now, your time reversal just looks around the fluctuation and talks how it goes up and how it goes down. Okay? You want to zero in and to see if I take a state that at this particular moment is very far from the thing. You know, here I just say that if I average over time, and because it's positive, I know that at almost all time is very closed. But you want to say, for example, in case of a thermal one, how does it look here? Because here I have my cup of coffee hot, and how exactly it goes down. This we haven't yet done. There are some developments along those lines, but those have not yet been done. Okay? So obviously I'm not throwing away everything, but there are questions that my approach doesn't allow me to address at the moment. On the other hand, what I found, we have some other results on the independence of the equilibrium state from the state of the environment, where if I, okay, so that can be proven again. Although you don't know how it will look, you don't have formally, you know, the way to compute this, because you don't know how to compute what the energy eigenstates are. But I can tell you that anything else doesn't matter for that in order to tell the fluctuations. So
No,
we,
this is, like I say, really
yeah.
beautiful and really profound.
So, but the thing that one thing that I really believe it is important is that people thought that things really fluctuate wild, and that is part of the dynamics. While my claim is that these things are much smaller. If you were to look at the fluctuations to perform measurements of rho of S, you would find here, you would, sorry, it's positive. You would find it all over the place. So those would be the big type of fluctuations that you are used from the thing. But they come from measuring something in a density matrix, not from changes of the density matrix itself. Lev, you work with your hand up from the beginning.
I understand that this calculation is supposed to tell us why the coffee during this 1 hour became colder.
Not exactly this, because in order to tell about this particular coffee, I would have to prove that almost every state of the air here is such that it leads to a large D effective.
But this is what it's supposed to help.
Yes, in this world.
But if I understand, all your calculations are unitary calculations.
Absolutely.
So you want to believe so, but this assumes that during this 1 hour, there was no one collapse or one splitting of the world. So then...
Okay, may I, just for the sake of my sanity, avoid going into many worlds.
No, but this is exactly
Maybe,
why-
okay,
No,
okay.
I don't do it with collapse or do it with many words. That doesn't matter. Whatever, it's...
Okay, so if
looks
you...
like that the idea that everything is unitary for 1 hour, for this cup of coffee in this room, I think it's
Fine.
not...
Yes. Look, I don't know.
realistic.
This was as you say very correctly, this was a unitary computation, and this is what it is. So I didn't say, but I could say the following. I could ask the following. Suppose I come and I collapse it, and then I want to see what happens afterwards. So when I collapse it, I will break this long thing, may take it from there, and then I know that on long term it will continue. Now explicitly I say I have at the moment that is, this particular computation tells me nothing as far as I presented about the time scale. So you will ask me, if I performed here a collapse and I took it out from equilibrium, will it equilibrate? And I say, yes, it will equilibrate. How quickly will it equilibrate? And I will say, you didn't listen to what I said, that I don't know. I don't know yet. So questions about the time scale, I believe, can be addressed, but they are much more complicated.
So this is just for a time scale until collapse happened? Some people say it's happened extremely often.
What is often, I don't know. I didn't put times, and again, as far as I presented here, there are further results, but I don't want to enter in all of them, and generally are not mine. They are Tony Short's and so on.
But you believe that all this, the calibration, that the collapse has nothing to do, so it can be explained. Even without collapses, the collapses doesn't help.
Okay, so the statement is like this. This is the result of a purely unitary evolution of the state. That's all that enters into the calculation. Collapses do not enter in the calculation that I presented.
And you didn't consider how...
I didn't consider...
You didn't consider is a collapse
I
important
did,
for
no, I did not. The only ingredient that comes in proving this is unitary evolution. That is very simple. I don't know who was next.
It was realized, I think, long ago by Lindenbell. There's something called Lindenbell statistics.
Yes.
That if you want to do statistics of gravitating system, you can't do Boltzmann. You have to do something else. And I don't remember what it was, but I remember the term Linden-Bell statistics, which is really different from the usual.
It must be different. It must be different because, so I don't know about that, but what enters, I don't have the full proof, but almost, that what enter into the thermalization, as we know, to Boltzmannian, is the fact that energy is an extensive quantity, and I can separate piecewise.
Your proof applies also for gravitating systems?
Yes, for any Hamiltonian.
It's much better.
Of course, it's much better. That's why I present it to you. I'm not wasting your time. It's far better. Just to make sure. Okay. And
Sandu, one trigger comment and one trigger question.
yes.
The trigger comment is that you said at some point that it doesn't matter what Hamiltonian you do.
It doesn't matter for the amount of fluctuations. For what the state is, for this omega, for that it matters.
Okay. So what my comment is that you may be correct, provided that this Hamiltonian breaks conservation laws of the system, of the isolated system. For example, if this Hamiltonian conserves the charge of the system, you will never be able to attain charge equilibration between the system and the environment.
Look,
So it should break all possible non-conservation laws.
well, here I'm talking about an entire system. So if you look, the system exchanges with the environment. The condition, which is very subtle as a matter of fact, is this. Take any Hamiltonian that you want. Pick anyone that you want. Perturb with infinitesimal thing your states. If it so happened that they were having resonances, as a matter of fact, one can prove equilibration even if there are some amount of resonances, but not too many. And just perturb it infinitesimally, and the equilibration comes. Only the time scale will be longer.
No argument about that.
The question is whether, you see, if you want to conserve the charge here, no problem. I believe that.
No,
So if you don't want to let.
I want to conserve. Suppose the system has
Ah,
a huge amount of charge, and the environment has no charge.
oh, and the charge can go out.
And if the Hamiltonian, that part
Yeah.
of the Hamiltonian that connects the system to the environment,
Yes.
does conserve, that does not allow for any charge tunneling between the system
That's
and the
not a
environment,
problem.
then this will not happen.
Oh, no. Equilibration will happen, but the equilibration will be around another state omega. It will not be around the one that you imagined, where the charge is now spread all over. So the question is, will it stop around, or, well, will it fluctuate very little around some omega? It's very easy to obtain that thing that you say. Suppose I take this one, and I put here around it, I don't know, some Faraday cage, or well, something that keeps charges there, doesn't allow charges to go. Suppose I put a lipid membrane, and charges will not go through. That doesn't mean that it doesn't cool. So the equilibrium will be attained, but is not the equilibrium that you thought with the charges spread. So that doesn't necessarily mean that I would have degeneracies here. But the thing that you are right is that the state around which it equilibrates will be different.
The quick trigger question I have is this. In order to understand
Yes.
a nice and complicated theory, I always like to go to pathologies, to explain
Yes.
cases.
Yes.
And here I have I want to compare two pathologies in your
Yes.
theory. One is when there is interaction
Yes.
between the system and the environment,
Yes.
and I prepare the world, the universe,
Yes.
in a product state of an eigenstate of this system times eigenstate of
Oh,
this
then it's trivial. Yeah.
And the second one will be that there is interaction, and I prepare the universe in an eigenstate of the system and universe.
Okay. So.
But the question is that I think that in both cases,
This doesn't apply. This doesn't apply.
will not be sensitive to
Indeed. However, if you prepare it without interaction, which is an extreme case, but it's a trivial case, and I tell you what happens. In that case, it does not need to equilibrate. It stays as it is, and it will evolve by itself. If you prepare it in an eigenstate, this is just a bound. So this bound will not apply, but I know what the result is in that particular case.
So
that it doesn't.
box does not apply.
My box will not apply to that, but I know for that particular case I have an ad hoc solution. Yes.
I'm going to follow Yuval with a comment and a question.
Yes.
The comment concerns your boxed formulas. So this quantity is
Yes.
well known in the quantum chaos literature. They call it the inverse participation ratio.
Yeah, of
And
course.
let me explain why it's interesting
Yeah.
that you come up with it. So if you take the limit of the coefficient
Yes.
Cn being chosen from a Gaussian random ensemble, then
Yes.
you'll get the dimension is the true dimension divided by 3
Yeah.
to do that sum. But if you take the other limit, where you have a highly localized state, then you basically all of the coefficients lie on one thing, the rest are 0, and you just get 1.
Yes.
So you can go from essentially 1 from the true dimension over 3
Yeah.
as the possible limiting cases.
Yeah. So as I said, in fact, it goes from 1 to n, where n is achieved when all of these are equal. If they are taken from a Gaussian, then no.
Then it's
Yeah.
over 3.
But the name of effective or participation, that is a very good name, because that comes out from the fact of really how much you scan when you move. You cannot look at the rank, because then it will be the entire Hilbert space, but sometimes you may touch a dimension just or almost 0.
So my question, Sandu, then is about in our community of the quantum thermodynamics, what's very popular these days is looking at something that my former PhD supervisor came up with called eigenstate thermalization hypothesis.
Indeed.
And in that scenario, you don't have a partition between the system and the environment. You simply have one system, usually taken to be chaotic. And by looking at subsystems, you can show an effective thermalization arises. Can you compare your approach to this ETH approach?
Well, so what is this ETH? What is this energy eigenstate thermalization? That says that if I look at energy eigenstates and I look how the system looks for those energy eigenstates, almost all of them look the same. If they look identical, then it's obvious that nothing changes ever. Okay. Now, in some cases, that may be correct. In some cases, not. That depends on the Hamiltonian. It is not a generic property when you get crazy Hamiltonians. It's definitely not. How often that happens, there are not very clear results, for how type of Hamiltonians and how often the energy eigenstates are like that. There are other approaches to this. An interesting approach that is a bit alternative to this is not to take, coming of what you say, a system and an environment, but just to look at a single big system. However, to pick any observable, A, and ask, what about A? What about the probabilities of this observable? How will they vary in time? Okay? In our case, those are the observable for the little system S. The result there is a very strong result by Riemann. is that pick any observable, and for almost all time, its distribution of results will be equilibrated. But of course, there are many observables. So at every particular time, there are many that are not at equilibrium. So that is an alternative approach. And I believe that using these two approaches, it goes. But one thing I want to say, this is not any approximation. This is an exact result. And it turns out that all you have to do is just, just see that a phase, if you average over time, gives 0. That's all it is. And why did I need to that issue of non-degeneracy? You see, ρ already has a difference of 2 energy levels because it's psi and psi. But you want here, you want this distance involves ρ square. So it involves 4 energies. So that's all that enters. That is the only ingredient. What was important was to make the concepts clear. And then that particular mathematical thing was easy. Looking how it goes in the time, now that is interesting, and that would be fascinating and goes out. All right. Good. So if no other questions, thank you.